These pictures were received from a direct broadcast by satellite. One day, we may all be receiving such transmissions at home, and direct broadcasting by satellite could change the face of television as we know it today. In 1975, NASA launched the ATS-6 satellite, broadcasting an experimental television service to the Indian subcontinent. At that time, a DX-TV enthusiast in Sheffield saw this as a challenge he couldn't ignore. With a signal strength in theory 30 dBs down on the main footprint over India, Steve Birkill was to succeed in resolving those transmissions using only surplus and home-engineered equipment. He's now able to watch pictures of this quality from a Russian Gorizont 4 communications satellite. The heart of the system is the head unit. Steve explains.
Feed horn. This is a scalar horn, which is a variable beam with feed. It feeds into circular waveguide. This section here is a polarizer. These stubs will produce circular polarization or produce linear from circular polarization, dependent on the orientation. This is the actual feed probe, which is a waveguide to coax transition. 12 gigahertz signal comes out of here, then coax to microstrip transition, FET amplifier, gallium arsenide FET in microstrip, first stage, likewise second stage, mixer in strip line, gun local oscillator on the low side of the signal. No, it's on the high side in fact in this one. First IF comes out here, IF head amplifier in there, first IF 450 to 950 megs. This is a wideband IF amplifier, 21 dB, 450 to 950. Output comes out here to feed to the house, and 12 volt supply from the house goes in here. The rest are just bias circuitry for the FET stages. This is for the OTS feed, which is Brian Haynes' transmission this week, his test transmissions to Europe.
I presume I need to make obvious to people that 12 gigs are really meant for broadcasters to pick up and receive from, whereas a 4 gig one, it's actually meant for the viewers to look at direct.
OTS transmits in the 11 to 12 gigs band. It's sitting at a frequency which is allocated for the fixed satellite service, but the eventual broadcast satellite service at 12 gigahertz is in a very close frequency band to this. We're talking about a 2.5 centimetre wavelength. And it'll be a similar head unit to this, except it will be rather more cosmetic. That will be used for DBS services within Europe, and in the States for that matter when they start.
This sensitive piece of equipment is protected from the elements by nothing more exotic than a plastic dustbin liner. The dish tracking system is simple but effective. It consists of Steve watching his own spectrum analyzer in the kitchen through the center of the dish, whilst adjusting the elevation and azimuth of the dish for maximum signal. A closer look at the spectrum analyzer reveals the satellite activity on the band.
And, because of its signal strength, they put energy dispersal on it, but it's a fairly unusual one because it's a 2 hertz triangular waveform, and the total deviation is about 5 megahertz or more.
Why do they do that? I can't see any advantage.
It reduces the spectral energy at any one frequency. The other channels, this one is Northern Hemisphere. Again, this is my estimation because the published information is a bit thin on the ground and not very reliable. This is Northern Hemisphere, and this is global beam. By global beam, I mean it illuminates the visible Earth as seen by the satellite. And this thing is just the marker to indicate where I'm tuned.
These pictures are from a Saudi Arabian communications satellite and are representative of what is possible at the limits of the system. The signal, being 100 times weaker than the earlier Russian signal, is comparable with the original results from the Indian satellite and was received on the Mark I equipment.
This was my satellite receiver for period 1978 to 1981, and this modular receiver took over in mid-81 and is of course capable of rather better. I mean, I only built that because from having access to signals of this sort of strength, I suddenly found I had access to signals that with an 8-foot dish would yield full quieting, like the Russian like OTS. So obviously I needed to take advantage of the better performance I could get. I wanted a receiver with something approaching professional spec, rather than this, which is all right as a narrowband receiver for experimental reception to see whether there's something there and what can be made of it.
How much are you narrowing the band by?
Well, it's variable bandwidth on this. The phase lock loop is operated below limiting, so the actual noise bandwidth depends on how hard you drive it. So it'll narrow, at maximum it stretches to about 15 or 20 megs. It'll narrow up to about 1 megahertz if I wanted to. I'm probably operating at something like 3 here.
The Mark II equipment offers greater flexibility.
Okay, it comes in at UHF. I shouldn't give my secrets away like this. UHF wideband amplifier, 450 to 950 is the range we're interested in. It splits in 3 dB hybrid to 2 down converters, switch selectable, full band and a narrow band with special AFC for the Russian energy dispersal. The IF outputs of these at 70 megs, selected by relay in here, 70 meg variable gain amplifier to set IF gain. Comes out of here through a 70 meg filter, 25 megs bandwidth, 3 dB bandwidth to define the noise bandwidth of the system, and then into a 70 megs IF amplifier, about 30 dB gain. From there into the video demodulator, an AFC unit, whose outputs include the subcarriers, the audio subcarriers, the video switchable polarity, and the AFC, which is fed back to the down converter. The audio is up converted, local oscillator and up converter, double balance mixer in here. The digital frequency meter on the front reads the local oscillator frequency less 10.7 meg. The 10.7 output from here goes into a commercial 10.7 meg audio demod, and then we have an expander for the Russian pilot tone companding system. I think that's it. And a commercial UHF modulator feeder standard TV. The sound is transmitted on a subcarrier at the top end of the baseband, which is an FM subcarrier. Wideband FM, similar to your standard intercarrier sound. But the subcarrier they're using on this transmission is about 6.6 megahertz instead of your 6, which is standard for the UK, or 5.5 for Western Europe. 6.6 is what they're using. I don't know why. I think it's probably just... No, I don't know the answer, why they're using that. It's a standard frequency that's used on OTS. I've seen it on OTS before. But by comparison, the Russians use 7 megs or 7.5. So I've got a tunable intercarrier demod in here, which takes the top end of the baseband, heterodynes it up to 10.7 megs, and demodulates it with the sort of technology you find in an FM receiver.
It started to rain, and
This is a test transmission from the UK-based Satellite TV Limited on 12 gigahertz via OTS-2. OTS-2 is a communications satellite being used to evaluate a European direct broadcast service. These signals are noisier than would normally be expected. This is probably because the test involved a low-powered uplink to the satellite. It must be pointed out that further degradation of the pictures occurred due to multi-generation recording impairments. Steve's pioneering efforts may soon bear fruit commercially in the USA when he takes up his new position in research and development into a viable home system.